So with this episode, we begin the chapter on magnetism. So we've seen so far that in the town of force field, there have been two main players. One is the gravitational force field, the second is the electric force field. So both of them work very similarly. You have a charge for the gravitational field, which is the mass. It's acted upon by the gravitational field, this gamma. So this gamma is basically gmm over r squared for the general case. And if you're near the Earth's surface, that gamma is simply the little g in value, in magnitude. In the electric case, the charge for the electric field is electric charge Q. If you place it in an electric field E, it feels a force. So instead of the m times the gravitational field, here you have the electric charge times the electric field. And this gives you the force over here. For the case of the point charge, that electric field is kq over r squared in the case of the point charge. But the thing is that all of these fundamental force fields, you have something that's causing the field, you have something else that's feeling the field, the victim of the field. And they're usually the same. Mass is what causes the gravitational field. And electric charge, the Q, is what causes the electric field. When you place another charge in its path, that electric field exerts a force on the charge. So with this chapter on magnetism, there's basically a new kid in this town. We have the magnetic force. So this force field behaves in a similar manner. The charge for this force field is very strange. It's the regular electric charge in motion. So if you have a charge, electric charge that's just sitting still, it creates an electric field. If you have a moving charge, it creates a magnetic field. And a moving charge in the path of a magnetic field feels a force. And that's the force. And that force is given by, unlike these two simpler equations, is given by the charge for the magnetic field, which is the QE, and crossed into B. So this QE cross B, that's a vector product. And we'll look into that in a little bit more detail. But first of all, the unit for the magnetic field in the MKSA system of units that we use for this course is a Tesla. So the unit for the magnetic field B is a Tesla, symbolized by the capital T, just like the car. And then there's another unit in common use. It's not our standard MKSA. That's the Gauss. It's a smaller unit. So 10,000 Gauss is worth 1 Tesla. Now there'll be situations in which both the electric and the magnetic field are present. In that case, both of them act on the charge. The electric field acts on the charge that's not moving, the Q times E from before. And the magnetic field B, it acts on a moving charge. But if you have an electric charge, you can have a combination of these. And these can be grouped together in a common electric plus a magnetic field over here. And then this total force Q times E plus Q times V cross B, this is equal to what's called the Lorentz force. And this is the Lorentz force law when you have both fields present. So mostly in this chapter, we'll be dealing with just the magnetic field. You'll have just one field at a time. In that case, you don't have this first QE part over here. You have just the magnetic part. And that part is QV cross B. And this equation here is called the magnetic force law. It is a law. There's no reason why this force should have existed. It just does. And this is the equation that describes it. And therefore, it's a law. And the QV combination, as mentioned, that's the charge of the magnetic field. Now, of the three fields, gravity, electric, and magnetic, under everyday terrestrial conditions, B is by far the strongest. There are more practical applications which are utilizing the force coming magnetically versus the force coming electrically or through gravity. So the electric force, as we've seen before, is a very feeble force. And if you brush your hair with a comb or something like that, I mean, you're doing well if you pick up a little piece of paper like this. Now, in the case of gravity, it may seem like a stronger force, like when you pick up a weight, like when you're exercising or something like that, you can feel how strong it is. But think of this. Look at this. This is a stack of 3 magnets. These are being pulled by the entire Earth. The whole Earth is pulling on this. And then you get this force. By comparison, look at how strong the magnetic force is. This tiny thing is nothing compared to the size of the Earth. But, you see, it's able to lift that magnet, the other magnet, very easily. So magnetic forces are very strong. They're short range, they act over a short distance. That's actually better for application. You have more control. You don't have the force spilling out all over the place. It's more specific where it's needed. So as a result, if you look at many applications that involve motion, rotation, and so on, electric shavers, refrigerators, blenders, vacuum cleaners, most trains are electric, and now even cars are electric. So as a result, in terms of practical applications that require movement, rotation, etc., the magnetic force is basically the winner. Now there's something very unique and unusual about the magnetic force. It has an odd direction. How so? In the gravitational case, the gravitational field is pointing down towards the center of the Earth, and the force is in that same direction. It seems very logical and intuitive. In the electric case also, if I hold a positive charge over here and I put a piece of lint or hair or something like that, it gets pulled in this direction. So the force is in the same direction as the electric field. If the charge is of opposite polarity, it could be opposite, but the line of direction is the same. Only the sense of direction can be different. The magnetic field is way odd. You have a cross product, which means the force is perpendicular to the field and the direction of motion. You may have previously encountered the cross product in the context of torque. The torque is R cross F. So the torque vector is perpendicular both to R and to F. What does this equation mean? So this is the business of torque. If you have like a screw over here, you're trying to loosen it, some kind of a nut, etc., then this is the force that's applied. This distance here, that's the R. The bigger the R, so instead of this tiny wrench over here, if I have something longer like this, I have a bigger R. I have more leverage. So as a result, the torque is going to be bigger. But nevertheless, my force is in this direction. The R is in this direction. So let's say this is my force and this is my vector R. So this is what these vectors look like. This is the force and this is the R. R cross F is a vector that's perpendicular to both. How do you get this? You bring the vectors, bring the tails of the vectors together as you always do. This is R, this is F. You curl your fingers from R to F, and the thumb points in the direction of the final vector. So this is the vector pointing at me, and that's the torque vector. So here's an example of the cross product. The final vector, the product, is perpendicular to both of the vectors that you cross together, hence the name cross. So the same kind of math basically belongs to the magnetic force. So let's see how. So let's see how the cross product works for a moving charge in a magnetic field. So this is a region of space where the magnetic field is pointing perpendicularly down into the plane of the paper. So this is my vector, is pointing straight down. So a vector that's going away from you, that's not in the plane of the paper, that's perpendicular to it, if it's going away from you, you show it as a cross. So think of this as a rocket that's moving away from you. At the end of the rocket, you have some fins, or if it's an arrow, you'll have some feathers. That's what the cross is intended to indicate, that it's something, a pointed thing that's moving away from you. On the other hand, a vector that's coming toward you, that's shown in this manner. So this is toward and this is away. So anytime you have to draw a vector that's not in the plane of the paper, you have two possibilities. Either it's coming toward you or it's going away from you. So going away from you, you're looking at the feathers, hence the cross. When it's coming at you, it's like a missile, an arrow, or bullet that's coming straight at you. So the last thing you see is a dot with a circle, before the lights go out. So this is how you draw vectors which are perpendicular to the plane of the paper, going in or going away. And nevertheless, here you have a region of space where the magnetic field is going into the plane of the paper. How do you do that? This is the south pole of the magnet. So, rather the north pole of the magnet. So the magnetic field comes out from the north. We'll talk about magnetic field lines later. In any case, the magnetic field lines come out from the north. So if I hold this magnet like this, there's magnetic field coming out of here and going into the plane of the paper. Now you have an electron moving in this direction. So here's the electron. So those of you who've never seen an electron, it basically looks like this. It's a blue circle marked with an E and a negative sign. So here the electron is going in this direction. And the magnetic field, as mentioned, is going in this direction. So let's figure out the cross product and its consequent direction. So with the field going in like this, the velocity in this direction, we want the direction of QV. But Q is negative and electron is negative. So as a result, if the velocity is this way, the QV is in the opposite direction because it's negative. So that's V. This direction over here, this is Q times V going in this direction. So hold the first vector like this. So my blue pen over here, that's going to denote my QV. The B is going down, as we already discussed. Move the vector so that the tails are together. So now the tails are like this. Let me hold it up over here. You see the tails are like that. And then the final result is always perpendicular to the plane of the first two vectors. What does that mean? The blue thing is my QV. This is my magnetic field. This is the plane of those two vectors. So the cross product is either this way or the other way. It's perpendicular to both. Now you use the right hand thumb rule to decide which way. So you curl your fingers from the first to the second. So what I'm doing is the following. I'm curling my fingers from the QV to the B, first to the second vector. My thumb is pointing this way. So that means the force is in this direction. So something like this, basically. Okay. So in this picture over here, here's my QV, and there's my here's my QV, and there's my B coming out like that. So as a result, the force ends up going in this direction. You see. So if the electron enters this region of space where you have magnetic field going like that, the electron is moving this way. The force on the electron will be downward. It's perpendicular to both. So think about it. How strange is that, right? Here's the electron is moving this way, and then you have a magnetic field going like that. Shouldn't the magnetic field push it down? No, the magnetic field pushes it in a direction that's perpendicular to both. Very odd behavior. Now, how do you know that's true? You can test it with an experiment. So this is a really cool experiment posted on YouTube by this channel over here, NPS Physics. So do look at it. I'll post the link in the description. But the point is, they have a cathode ray tube. You see there's a beautiful glass tube over here. There's a filament here that boils of electron. It's attracted by a positive plate, so it's accelerated. It's focused into a narrow beam. And you can see that beam over here. You see the blue beam? That's the electron beam going across, and it hits the surface over here. This is how TVs used to work. It's called a CRT TV, cathode ray tube. So that's how these things work. And in the case of the TV, the beam was basically swept around to create the picture. So we actually own such a TV in our home even now. But the point is, now what they're going to do in this demonstration is they're going to poke a magnet perpendicular to the beam. The magnetic field is going to be horizontal, as you'll see. Nevertheless, instead of pushing the beam away or toward, the beam gets deflected downward, perpendicular to both, the cross product. So let's watch more of the video. See, when they bring the magnet close to it, the beam is pushed down. How odd is that, right? You have the magnetic field shooting out from the North Pole. Instead of pushing the beam away, the beam is basically pushed down. Very odd. And that's the cross product business that you have. The second time he brought the South Pole close to it, so the field direction was reversed. So here's one of those pesky thinker questions. Why does this happen? So you have the odd direction between the force, the velocity, and the magnetic field. So in that demonstration, the electron beam was sort of coming towards us. The magnetic field was this way. So instead of pushing the electron beam away or towards or something like that, it gets pushed downward. So the force is perpendicular to both. So see if you can come up with a reason or an explanation for why the force has a funny direction that it does, perpendicular to both. So the short answer is no one knows. No one has a clue. It's a physics law. This is the magnetic force law. It just does. So remember, a law is an observed pattern of behavior. That's just the way nature behaves. How, why, who knows? So anytime you can derive or explain something, that's a law. At least at that point in history and in this point in the development of the subject, it just is. So nature doesn't always have to be intuitive. Nature can do whatever it wants. We are kind of just there for the ride. Incidentally, if you do sailing, this is not so surprising. If you have in the case of sailboats going parallel to the shore, parallel to a beach, the wind is usually pointing towards the land. You have a sea breeze that's perpendicular. You'll often see boats going in a direction parallel to the beach, even though the wind is perpendicular. So it's quite common to have motion that's perpendicular to what seems to be the force. In the case of the sailboat, of course, there are additional forces because of the rudder and stuff like that. So now let's bring this all together by doing an example. Let's see how this magnetic force law applies. So in this picture over here, you see what's called a bubble chamber. You have basically a chamber. It's filled with liquid hydrogen. When charged particles go in, so they use this for experiments involving nuclear physics, high energy physics, and things like that. So you have a particle going in horizontally. When this particle goes to liquid hydrogen, it creates a trail of bubbles. You see those white tracks in that black liquid? So that's the black stuff, that's the liquid hydrogen. Those white lines, those are trails of bubbles. So this thing is going in, it leaves behind a trail of bubbles. So you can basically find out its path. Now the magnetic field, as you'll see, is pointing straight up like this. So if let's say it's a positive charge, it's moving this way. This is my QV, this is my B. So the force is going to be QV cross B towards me. So if this is the force vector here, this is going to point towards me. Now if something is moving in one direction, if you have a sideways force, it's going to cause this thing to turn. And that's the reason why you have those circles, you have those curved paths over there. So now, so we can basically get the magnetic force from the previous equation that we saw, the magnetic force law. We can apply the fact that the acceleration is the centripetal acceleration, the v squared over r, and put things together. So what are they asking here? So you have a charged particle moving through the bubble chamber, travels with a circular arc. They give you the radius. 0.5 meters is the radius of those curves. And the magnetic field which is applied, which in this case is going vertically upwards over here, the value is 0.1 Tesla. What's the momentum of the particle? They give you the charge of the particle as well. It's minus 1.6 10 to the minus 19. That's basically the electronic charge. So let's see how you work this out. So here's what it looks like in a diagram format. You have the electrons are going this way. That's the velocity. They're going in an arc. They're going this way. But the QV is the opposite to that in direction. Because the charge is negative, if V is this way, a negative of V is going to put it this way. So that's your vector QV. Then the magnetic field is pointing straight up like this. So here's the magnetic field. And so now the force, it has two choices. It's going to be either this way or it's going to be this way. It's perpendicular to this plane of these two vectors. So it has only two choices. So which way is it? You curl your fingers from the first to the second. So QV is the first vector, B is the second vector. So you can't curl this way, it'll be going backward. You have to curl from this to that. And notice that my thumb ends up pointing to the left. So that's the direction of the force, this thing over here. So this gives us the direction of force. This comes from the right-hand thumb rule. As far as the magnitude of that force is concerned, the vector QV cross B, the magnitude is QVB sine theta. Theta is the angle between the magnetic field and the QV. That's 90 degrees because the electrons or other particles, they're coming in horizontally. The magnetic field is straight vertical, if you saw in that bubble chamber picture from before. So as a result, you have 90 degrees. So that's good. Sine of 90 is simply equal to 1. So now break this force into vectors. So the things are moving in two dimensions. So you want to be clear what direction means what. So here's my x and my y axes. So the force, as you saw, was going, so force is green. This force is going to the left. my x-axis is to the right. So based on this diagram, the official angle of the force vector is 180 degrees. And so remember that. So let's now see how the vector equations break down. So you have sigma f is equal to ma. For the x-axis is sigma fx is equal to max. So as far as adding forces is concerned, there is only one force or only one player in this game right now. So that's the magnetic force. So that, as we just said, is Fb. The x component is cosine of theta. The value of Fb, that's equal to QVB. Cosine of 180 degrees, remember we had the 180 degrees for the x component. Cosine of 180 is -1. That's where the minus sign is coming from. So the x component of this magnetic force is equal to minus QVB, minus because it's to the left, x is to the right. Now for the acceleration, this acceleration, the x component is the total acceleration times cosine of its angle. And as you can see, the acceleration is also to the left. This thing is making a left turn over here. So the acceleration is pointing towards the center. The value is v squared over r is the centripetal acceleration. So this thing is a sub c, this centripetal acceleration. And so you have this business here. Again, the cosine of 180 will generate a -1. So this ends up being m v squared of r with a minus. So equate the x component of the force to the x component of the acceleration. So that's I've done that here. You have minus QVB is equal to minus mv squared over r. Cancel the negative signs and move things around. You can also cancel a v. There's a v here and a v squared. So one of this v is gone and a v squared becomes a simple v. M times v is the momentum. So mv, this is what's called p. That's the momentum. So rearranging this equation, mv, which is the momentum p, that ends up equaling qrb. And if you put in the values, they gave you the charge, 1.6 10 to the minus 19. They gave you the radius. They gave you what b was. Crunch this out. And this is the momentum, if you prefer. And that's equal to 8 times 10 to the minus 21. The unit for momentum is mass times velocity. So it's kilogram meters per second. So this is an illustration of how you would apply the magnetic force law to a problem. So far we've talked about charged particles moving in a magnetic field, individual charged particles. But you almost never encounter that situation in the most everyday application. Who owns a bubble chamber? And very few people own a cathode ray tube or TV anymore. But more commonly, you'll have a wire carrying a current, which is placed in a magnetic field. So here's my magnetic field. So this is a much more common situation. There are wires all over the house. Everyone's house is filled with wire, and you have magnetic fields. So you can have a force. Now, true to its character, the magnetic force is odd. When in the case of a wire carrying a current, you have a cloud of charges which is moving this way. If you apply a magnetic field in this direction, you don't push it away or pull it toward. Instead, you lift the wire up. So we can calculate the force on a wire carrying a current based on the magnetic force law that we already have for a single charge. You have many charges moving here like a cloud. You can add the forces on all of that on the total charge that's moving and calculate the force on a wire. So let's now look at that derivation for the force on a wire carrying a current. So let me briefly interrupt that derivation with a quick demonstration. So here, this was extracted from a YouTube short. You have a wire going through a magnetic field. You'll see that when the current is turned on, the wire jumps up. So you have this transverse force on the magnet. So let me go ahead and play this video. You see, so every time the current passes through the wire, the magnetic field is perpendicular to the wire basically hops up. Okay, so with this brief commercial interruption, let's get back to our derivation. So here it is. This is a wire, it's carrying a current I, that constitutes lots of little charges that are moving, usually electrons. Sometimes they can be positive charges in some situations as well, but usually they're negative electrons. No matter, let's assume for simplicity that they are positive charges. Sometimes they can be. So the current is flowing to the right, the charges are moving this way. So here is my QV vector, the same as the current vector I over here. Now let's say within a length L, the total amount of charge that's moving, that's this capital Q over here. So it's a collective charge in this section of wire whose length is L. And the magnetic field here is pointing inward. So that's the direction of the magnetic field going in. This is the direction of the current, which is the direction of this collective QE. What's the force on here? So the force is given by QV cross B. This Q is the sum of many charges, but doesn't matter. Now the velocity, you can relate that to the current. So V is the displacement over the time. So you can replace the V over here by the length L divided by the delta T, the time it took for the current to move from there to there. And you still have the cross B on this side. Now regroup this. So the delta T was under the L, move it to be under the Q like this and keep the L separate. Now Q over the time, that's the amount of charge that's flowing in a certain amount of time. Rate of flow of charge, that is the current. So you can replace this whole parenthesis Q over delta T by I. So now this becomes IL cross B. And this is the force equation for in the case of a current going through a wire. Instead of QV cross B, you have IL cross B. And so this is the full vector equation. It gives the direction. So in this case, the B is going like that. The current is going like that. Bring the tails together, do a QV cross B, and then the force ends up being in this direction. So this works the same as it did for the individual charge. You replace QV with IL. And for the magnitude, the cross product is the whole thing times the sine of the angle between them. So in many situations, as we've seen so far, you have a 90-degree angle between them. The current goes one way, the field goes another way. Often you have 90 degrees. But even if you don't, just put that angle into the sine theta, and you'll get the actual value. And as far as the direction, we use the right-hand thumb rule, as I just illustrated. So IL cross B, it replaces QE cross B in situations where you wire through a current rather than an individual charge just moving through space. And this is a more common example. So speaking of examples, let's now do a typical example involving the magnetic force on a wire. So here it is. There's a horizontal wire 30 centimeters long. It makes an angle of 45 degrees with a magnetic field of 0.05 Tesla that's horizontally directed north. So the magnetic field is directed straight north. The wire is at an angle of 45 degrees and it's going from southwest to northeast. So it's going this way from southwest to the northeast direction. So this is basically how these things are configured. You have a 45-degree angle between them. And what's the question? What are the magnitude and the direction of the force on the wire? The wire is carrying a current of 2 amperes. So let's see how this works out. So here's the force equation. The magnetic force is IL cross B. The magnitude of that is ILB sine theta. This is the magnitude only. And then use the right-hand thumb rule to fill in the direction. So just put in the numbers. 2 amperes was flowing through the wire. So here's the magnetic field going like that. There's the wire going in the northeastward direction. This wire is carrying a current of 2 amperes. The length of the wire, the L, it's 30 centimeters. To convert that to our standard units of meters, so it's 0.3 in meters. So this is in meters. And then times the magnetic field, the B they said is 0.05 Tesla. And then sine of the angle between them. That angle, as you can see, this is B and that's I, that's 45 degrees. So crunch this out. This gives you a force of 0.206 and everything being in standard units, the answer is in the standard unit of a Newton. So that's the magnitude. And as far as the direction is concerned, here is the B and there is the I. So you curl your finger. So first of all, the final result the force, it has only two choices. It can either be this way or it can be going into the plane of the paper. Because the vectors are in the plane of the paper, the answer has to be perpendicular to the plane of paper. So it's either inward or outward. So now you're supposed to curl your fingers from the IL or QE direction to the B. So when you curl your fingers, the thumb is pointing up. So therefore, that's the direction of the force. And we show an upward vector coming out of the paper as a circle with a dot. This is what basically a pencil looks like, or a missile will look like, before it basically hit you. So this is how you do a typical example involving the magnetic force on a wire.